In this video, we meet Euler circuits, walks that use every edge of a graph exactly once. The story starts with the 7 bridges of Königsberg, the puzzle where graph theory itself began. This is Königsberg. In the year 1736, the river Pregel cuts the city into 4 pieces of land. 7 bridges connect them. Watch them light up. The townspeople had a riddle. Can you take a walk that crosses every bridge exactly once and brings you back home? Leonhard Euler saw that only the connections matter. The shape of the land, the length of a bridge, none of it counts. So each piece of land becomes a single point. And each bridge becomes an edge between its 2 lands. Where 2 bridges join the same pair of lands, the graph simply keeps 2 parallel edges. This drawing is a graph, and this little puzzle is where graph theory began. Let us give the object a name. An Euler circuit of a graph is a closed walk that uses every edge exactly once. In other words, draw the whole graph ending where you began without ever lifting your pen, a one-stroke drawing. For example, this graph has an Euler circuit. Every vertex here has degree 4. Watch the pen trace it. All 12 edges, each used exactly once, and the walk ends exactly where it started. Back to Königsberg. The riddle now reads, does this graph have an Euler circuit? Before answering, let us see what having an Euler circuit forces on a graph. Take any vertex V and follow the Euler circuit as it passes through it. Each visit arrives on one edge and leaves on another. The visit uses up a pair of edges at V. 3 visits, 3 pairs, and all 6 edges at V are used. In general, the degree of V is twice the number of visits. The start vertex is no exception. There, the very first departure pairs up with the final return. So we have a necessary condition. If a graph has an Euler circuit, then every vertex has even degree. Let us bring that condition back to Königsberg. Count the bridges at each piece of land. In graph language, the degree of each vertex. 5, 3, 3, 3. Every single degree is odd. The condition fails everywhere at once. So no Euler circuit exists. The Königsberg walk is impossible. And that is exactly what Euler proved back in 1736. Remarkably, the converse holds as well. Euler's theorem says a connected graph has an Euler circuit if and only if every vertex has even degree. One direction we have already proved. Every visit uses edges in pairs. The other direction needs a construction. We must actually build a circuit. The idea is due to Hierholzer. Walk until you get stuck, then splice in detours. Here is Hierholzer's algorithm and a graph to run it on. First, check the degrees. Every one of them is even, 2 or 4, so the theorem promises a circuit. Step 1. Start at A and walk wherever you like. The only rule is to never reuse an edge. Look at E. We arrived on one of its 2 edges and the other one lets us leave. Even degree means no dead end. Back at A, the walk is stuck. Both edges at A are now used. We have a closed tour. But 9 edges are still unused. The algorithm does not restart. It extends the tour. B lies on our tour and still has unused edges. So we take a detour from B. By the same parity argument, the sidewalk can only get stuck back at B. It is a little closed tour of its own. Now splice, follow the detour when the tour reaches B, then continue as before. Watch the numbers update. 6 edges remain, and this time C offers a detour. Notice that this detour even passes through D, a vertex already on the tour. That is perfectly fine. A detour can only get stuck back at its own starting point, C. Splice once more at C, and now every edge is on the tour. Here is the finished Euler circuit. 14 edges, each used exactly once. At no point did a walk leave us stranded. That was the even degrees at work. And nothing here was special to this example. The construction works in every connected graph with even degrees. That proves Euler's theorem. How fast is this? The walk crosses every edge exactly once, and with adjacency lists, the next unused edge is found in constant time. So the total running time is linear in the number of edges. A small variation. If the walk may end at a different vertex, it is called an Euler trail. A connected graph has one exactly when it has 0 or 2 vertices of odd degree. Here is the classic envelope puzzle. Can you draw this figure in one stroke? Check the degrees. 3, 3, 4, 4, 2. Exactly 2 vertices are odd, the 2 bottom corners. Why does the corollary hold? Join the 2 odd vertices by 1 extra helper edge, the dashed one. Now every degree is even, so Euler's theorem guarantees a circuit. Let us build one, making sure the helper edge is the very last edge we walk. And there it is. An Euler circuit of the enlarged graph closing through the helper edge. Now delete the helper edge. The circuit loses exactly its final edge. And what remains is an Euler trail from one odd vertex to the other. So the envelope can be drawn in one stroke, but the drawing must start and end at the odd corners. Inside the walk, every arrival pairs with a departure. The 2 odd vertices are simply the loose ends. One last variant, directed graphs. A strongly connected digraph has a directed Euler circuit exactly when, at every vertex, the in degree equals the out degree. Every edge is now one way. Check each vertex. Do arrivals match departures? Balanced everywhere, so a directed Euler circuit exists. There it goes. It is the same pairing idea, just oriented. Every arrival needs its own departure. Thanks for watching. If you enjoyed this video, please like and subscribe to support the channel. More graph theory videos are coming soon.